Hi, welcome back. Today's video is going to deal with some conceptual background that we need to understand more advanced organic reactions. So we need to lay some groundwork here by discussing some concepts and some ideas before we can move on to more advanced chemical reactions. So today's video is really going to be about molecules as 3D objects, which sometimes can get lost when you do things in 2 dimensions on a whiteboard, or as I'm doing here on a piece of paper. So we're going to talk a little bit about isomers. And I'm going to talk about isomers in general, and then I'm going to go into how we can treat them as 3-dimensional objects and some of the consequences of the fact that they are 3-dimensional objects. So the most basic type of isomer is then a conformational isomer. I'm sorry, I'm going to end up talking about conformational isomers what are sometimes referred to as configurational isomers or geometric isomers, and then a subgroup within that, stereoisomers. As I said, geometric isomers are sometimes also called configurational isomers. I'm not going to go into that right now. But first, let's go back to what an isomer is then. So an isomer basically, or isomers, I should say, are molecules that share the same molecular formula, but where the arrangement of the atoms differ. So they basically have different structures basically. So even though I'm going to talk mostly about these types of isomers later on in the video, we can call this a third type, even though it technically is a part of this one. We can kind of outline the type of isomers that exist. And in organic chemistry. So there are 2 main types. We have stereoisomerism, and then within this we have then 3 groups. We have conformational, geometric, and optical. Those are the ones we'll deal with mostly in this video. But it is worth reminding people, if they have not had this experience before, that there are also things called structural isomers. And structural isomers can be divided down into 3 main groups as well: chain, position, and functional group. Isomers. Now I'm going to go through and basically go through all these types, and I'm going to do these 3 rather quickly. So I'm going to start by talking about those three and then move on. So first, and then we'll do this second. So that's real clear what we're dealing with here. So let's deal with the structural isomers first. So let's look at that. So we'll give it a heading here, structural isomers. And the most basic type then are what we call chain isomers. And basically then you take the carbon chain and you rearrange it. And sometimes these are also called branched isomers, right? And so let's look at one. Let's look at butane, for example. Butane has 4 carbons in a chain. So this is just butane. But if you rearrange one of the positions here, and you take one of the carbons and you move it and make a branch, then you have the same number of carbons. So you have basically 4 carbons here and 4 carbons here, and you get 2 methyl propane. 1, 2, 3 propane. And the methyl group is on the second carbon. So this is a chain isomer or a branched isomer. I'm not going to go into too much detail with that. That might be the subject of another video. And then we have position or positional isomers, which are related to this, but oftentimes have then some sort of substituent that is not an alkyl group, is not a carbon-based branch, basically. So let's look at this one. Let's look at an example here with a pentane, a chloropentane. So let's do it with a chlorine there on the second carbon. And then let's make this a chain that's a little bit different than the one above. So there we have 1, 2, 3, 4, 5. So this is going to be 2-chloropentane, because the chlorine is on the second carbon. If you do another one, same, basically an isomer. So it's going to basically have exactly the same atoms, but just arranged slightly differently. This molecule obviously is not exactly the same as that, even though it has exactly the same number of carbons. There are no different types of bonds or anything. It's just a different isomer. So this is 3-chloropentane, because the chlorine is attached to the third carbon. The third type of structural isomer is called a functional group isomer. And there are quite a few different types, and I'm only going to give really 2 examples here, or a total of 4 molecules, but 2 examples. So let's start with a simple alcohol like propanol. So here we have propanol, and then we'll draw another molecule that has exactly the same number of atoms, but is not. So this is C. Let's look and see the difference. So this is going to be an ether. So here we have propanol. And here we have methoxyethane. Which is probably more properly called, what is it? Methyl ethyl ether. right? These are the same. So here's propanol. They have exactly the same number of atoms, and they don't have any different types of bonds or anything like that, but they have different functional groups. Here we have an alcohol, and here we have an ether, which are quite different. And then we can look at another example really quickly before we move on. We can look at a molecule like propanoic acid. CH3, CH2, C double bonded to an oxygen and an OH group, like so. This is propanoic acid. And we can look at then in a similar molecule, or a molecule that has the same molecular formula, but is completely different, although it shares some very superficial similarities. So here we have then 3 carbons, an double bonded oxygen, a single bonded oxygen, so forth. But this one is called then methyl ethanoate and is an ester. Whereas this one is a carboxylic acid. So these are then examples of functional group isomers, where you can see that they're isomers, but they have different structures. And this is sort of a very quick run through of that, because we need to move on to the main part of this video, which is going to then deal with stereoisomerism. So basically, stereoisomerism is a way of describing molecules in terms of their three-dimensional orientation in space. And the most simple of all of them, I'm going to write up here if I can spell anymore, stereoisomerism. So the most basic type of stereoisomerism is called conformational isomerism. And this is due to the fact that single bonds can rotate. So if you have 2 carbons bonded to each other, for example, and I can draw them really quickly here. Let's say we have a carbon atom and another carbon atom with their substituent parts. It doesn't matter what their parts are, these little things that are sticking off of here, right? We can just put R groups on there, representing then that they can be anything that starts with an H or starts with a C. So one of the aspects of the single bond is that it can rotate freely, or freely with some modification, I should say. We'll get into that just a little bit, but not too much. Right? So because of this, you can have this situation where the different R groups end up in different positions relative to each other. So if this is R1, R2, R3, and this is R, let's say 4, 5, and 6, depending on how these rotate, how this bond rotates, the R1 could be directly across from this R4, or it could be directly across from the R6 or R5 for that matter, or it can be in between the two of them. And so you get then the definition then is the different three-dimensional arrangements of atoms resulting from rotation about a single bond. And that may not seem like such a big deal, but it actually can be quite, it can have quite a significant effect in some cases. So I'm going to illustrate it just a little bit quickly then with one example, and then we can move on. So let's say we take and draw a molecule similar to that one, and we just simply draw the different bonds. I'm going to put the carbon in the middle here. I'm not going to illustrate it very more than that. So if we try to visualize this three-dimensionally, where the dashed line represents the dimension backwards behind here, and the green, the thicker green line, represents an atom that is sticking out towards us, and the black line and the red line are in the same plane as the paper itself. Then we can see that if there's and I'm only going to do one example here, but you can see that if there's a rotation about this bond, then these things will end up in different positions all the time. So you end up with a situation like, if this one rotates, if we say that the red substituent, or the red part, stays exactly where it is right now, we can end up with the bond, or the atoms, moving around that central spot. So you get this transfer where the bond rotation occurs, like so. And so it turns around, it spins, and which is kind of interesting, because it leads to sort of little different types of problematic situations, or not so many, but it gives complicated molecules a lot of different possible conformations, because obviously here we're dealing with one atom and one bond that's rotating, and the same thing in the picture previously. But you can imagine then, if a molecule has many carbons, and these different groups have different characteristics, then the rotation of the molecule can have favorable conformations where all these different things line up in a nice way, and where they don't repel each other or they attract each other, or they can be, and there can be several of these different positions. In fact, one quite famous one is acetylcholine, which has two different conformational aspects that cause it to bind to different receptors, actually, in the nervous system, which is kind of an interesting property. So if we just take, for example, our example up here, we'll just quickly go through one here, and I can show you then what I mean by that. So if we take and we just look at this from kind of an oblique position, and don't worry too much about the reality of this picture, but sort of like more like think about it in terms of how it try to represent it so that we can understand what's going on, rather than trying to reflect reality too much. We can draw this one again. So this is one position, but in the next position then you will find that if these three stay in the same position or relative position, we draw them in the same relative position, we can see then that the next time, you know, the drawing could look like this, and then you would have so here the bond has rotated and they're in a different position now, and this can have some significant change. It can cause these different types of conformational isomers to have different characteristics, and certainly it does affect reactivity in more advanced organic chemistry. Then, and I'll just give a really brief example of one where you have a ring, for example. If you have a five, let's look at a 5-membered cycloalkane, which is normally drawn like this. This is cyclopentane. Well, it has a stable conformation like this, or relatively, but you can also imagine then that, for our sake just today, that you could have a situation where it could also be drawn like this. And in fact it does. It oscillates between different conformations as such, back and forth. And this might be stable, and this might be stable, but the in-between part is non-stable or not stable. So that's a little bit about conformational isomers. We'll move on to the other types of stereoisomers and look at them as well. So the next type of stereoisomer that I'm going to look at is something called a geometric isomer. So this is the second type. These are also sometimes called, as I mentioned earlier, called configurational. So these are isomers that have become fixed in a specific position relative to each other due to some kind of constraint. So here we do not have free rotation. So we can write that at the beginning, so no free rotation. That is the main thing that characterizes geometric isomers. So I can write the definition then, right? Isomers where atoms become fixed in specific positions right? Relative to each other. And this is due to some kind of due to some sort of constraint, due to some kind of constraint. And by constraint I mean something that hinders it, stops it, right? That prevents rotation. And usually this is a ring, or even more commonly it is a double bond, or at least more commonly in the way I'm going to talk about it. So let's look at how this can possibly be true. Well, let's just take an example with a double bond here, and we'll just draw it really quickly. So if we take and we draw a carbon with a carbon, and they're double bonded to each other, you draw them like this, and you put R1, R2, R3, R4 on here. Remembering that R is just means it could be hydrogen. It could be anything that starts with a carbon or it's a hydrogen, right? This bond does not rotate. So there is no bond rotation. And you can see this can also be occurring in situations where you have a ring. So let's take a situation where you have, let's just do a cyclobutane here, and you have R. We'll just do exactly the same setup. We will ignore the other ones for now. The ring will not allow this bond to rotate either, because then you have to sort of flip the whole ring inside out, and you can't do that. So there's no rotation. There's a constraint. And it can't be done. So this means then that R1, R2, R3, R4 are in fixed relative positions. They can't be done. Nothing can be done about them. And traditionally, when we've dealt with these types of molecules, or there's two different ways of dealing with these types of molecules, really. And one of them is a little bit more simple, and one is a little bit more general. And there's two different ways of naming these types of geometric isomers. Because of these locked positions, then, if you have a situation like the following one, you have, I'm just redrawing the same molecule again, basically, or the same picture again. If you take this and you say, and this time I'm just going to put XYZ on here. So this is, or no, I'll just do R1. R1, R2, R3, R4. The position of these two to each other, like this, is said to be trans. So they're trans to each other. Whereas if you look at the position of these two to each other, they're said to be cis. And this just means same, and this just means different. And how you determine which one is going to be which, you just look at them and you can say. So that we'll do an example here really quickly where we take a real molecule. We'll take C and we'll put Cl here, Cl here, and then we can say, aha, well, these are trans to each other because they're across the molecule like such. So this is going to be trans 1,2 dichloroethane. Whereas if I drew a molecule like this one, where both the chlorines are on the same side, like this would be cis 1,2 dichloroethane. And they're a little bit different. There is a problem though, because you can have molecules like the following, which kind of throw a wrench into this kind of system that we have here. So if we look at one that's kind of problematic, you would look at something that looks like this. Where you have three significant substituents on it. Sorry, that's an H. Now this isn't even a particularly complicated molecule. This is just, 1, 2, 3 chloro 1, 2, 3, 4, 5 pentane or whatever it is. 1, 2, 3, 4, 5. Sorry, hexane. Hexene. So you need to be able to figure out how this works, because in this case you have this problem of, okay, is it cis because of this? Or sorry, is it trans because of this, or is it cis because of this? And so there's been developed in an entirely different way of dealing with this, and I'll deal with that in just a second. And this is called the EZ method. So we have one type was called cis-trans, And now I'm going to talk a little bit about the EZ. In order to talk about the EZ system, or we should write down what they mean entgegen and zusammen, which are just German words for, against or and together, or not together and together. To talk about these, though, we need to talk about prioritization. So we need to learn how to prioritize substituents. And remember, a substituent is basically anything on a carbon chain or anything on a carbon that isn't just a hydrogen. So a substituent can be an alkyl group, meaning it can be like a methyl, ethyl, propyl, or it can be a chlorine, or it can be an oxygen, it can be a nitrogen, it can all be all sorts of things. But we need to learn how to prioritize substituents. And the prioritization rules are based on the atomic mass. So it doesn't matter what it is. As long as you know the atomic mass, you should be able to figure it out, right? It's the atomic mass of the atom bonded to the isomeric carbon. And by isomeric carbon, I mean the one that gives rise to the isomerism issue. So it can, in this case, it can be either of those, or there can be several different types. But the prioritizing rules actually work for other types of isomers as well. So it's important to learn this. So, for example, if we just take this simple case here, we can take, well, we know that hydrogen has the lowest priority, and it's going to be lower than carbon because carbon, has a, and it's going to be, carbon is going to be lower than nitrogen, which is going to be lower than oxygen, which is going to be lower than chlorine, which is going to be lower than bromine, which is going to be lower than iodine, which are the most common ones that are attached to these, for our examples at least. So that's not an issue. We can easily prioritize them between different, if we just have one atom. The problems arise when we have more than one atom. So if there are more atoms that start with the same atom on the branch. Now that wasn't exactly the best way of describing it, but I'll do my best to explain it over here. So let's say let's do this example first. It's easy enough to prioritize Cl and hydrogen and methyl group and then a bromine. We can see easily then that bromine has a higher priority than chlorine because bromine has a higher atomic mass. So this is high and this is low if we compare those two. And if we compare these two on this side, this is going to be low and this is going to be high because this one has a higher atomic mass. Carbon has a higher atomic mass than hydrogen. Fair enough. But you can also have situations like this one where you have something where you have an alcohol on it. It doesn't matter what it is. What do? Which of these two is prioritized? They start with a carbon, they both have an oxygen attached. And then you have, I don't know, you can put, let's not worry too much about this side. Let's leave them the same. Now, how do you know which one of these is prioritized? Well, it turns out that the trick is to think of this as a carbon that is bonded to two oxygens. So you have to have a mental picture. So you have to think that if they're the same, basically the same, then you have to think of this carbon as being bonded one time to an oxygen and then bonded another time to an oxygen, and therefore this has a higher priority. So this is high and this is low. And as you can see, as I've organized these, you can kind of see how the EZ system works. The EZ system works basically by taking the double bond. If we take the double bond again here, and we'll go back to our example where it was a little bit unclear. We'll say we have this, and then we have a chlorine over here, and we had ethyl coming off of here, and then we had a hydrogen and a CH3. Now, how do we name this thing according to the EZ method? Well, we just look at it and say, okay, which of these two on this side, we divide the bond in half and say, on this side of the double bond, which of these two has the highest priority? And this one has high, and this one has low. So let's circle that in color so we can see it. And on the other side, we have the first atom that is attached to this carbon is chlorine and carbon. So this one is high, and this one is low. And since the two high priority ones are on the same side, are like this, then this molecule is a Z molecule. On the other hand, if you have some situation like the following, where you have, I'll do something very similar, so it's fairly clear. This molecule would be the other opposite, right? Because here you have the high priority is here, the low priority is here, here the high priority is here, and the low priority is here, due to the fact that the first atom that is attached to this carbon has a higher atomic mass, so this is higher. So if you have this situation, then you have an E molecule. So it's similar to the cis-trans model or way of naming things, but it's a little bit more general. It can actually help you name molecules that are a little bit more difficult to name or characterize as geometric isomers. So the last type of stereoisomer is perhaps the most difficult to illustrate on paper, but is also one of the more interesting of the most interesting of them. So let's look at that for a second here then. We say the last of the type of stereoisomer is called an optical isomer. But there's lots of fancy names that you're going to have to learn for this one. So, right? So these are basically molecules that are what we call handed. That means that they cannot be superimposed on each other. A little bit like your hands. So I'm going to demonstrate it with this. If you have a molecule that has basically the same structure, right? But slightly different way of arranging the different parts in 3 dimensions, then you can have a situation where they're exactly the same and they're imposable, meaning that you can put them on top of each other and they have exactly the same structure, or they are non-superimposable, and when they're non-superimposable, then they are what we call handed or chiral. And this gives rise to a lot of different issues in organic chemistry, particularly in pharmaceutical problems and biochemistry and stuff. So I'm going to basically write what this means then. So basically this is when molecules right, or a molecule that is asymmetric about a central carbon and this usually means then, and I'll just write what that means, that these have 4 different groups or atoms attached. Right? So molecule that is asymmetric about a central carbon, that means that basically these have 4 different groups attached to them, right? And if that's the case, then these kinds of carbons, all right, these carbons are considered, or I should say these carbons are considered chiral. Now chiral is just a word, it means literally hand in Greek. So the minimum requirement then for a chiral, or for a stereo optical isomer then is that the original molecule, or the molecule that it's based on, then the standard formula means that there are at least 4 different things attached to it. So there has to be like 4 distinct substituents attached to a central atom, like so. And so to go further with then sort of the definition, then you can say that an optical isomer is when the atoms about a central asymmetric carbon are arranged such that the 2 cannot be superimposed on each other. And when you have 2 of those, the 2 different forms, these are actually technically referred to as enantiomers. So let's look at how that might work. And sometimes it's better to illustrate it. Some of these definitions become more clear when you see the drawings in front of you. So I'm going to draw then in different colors here to illustrate this phenomenon. So the central atom there is, I'm not going to draw it too much in detail there, but so if you have this situation, and once again reminding everyone, if the bond is drawn as a wedge that sticks out, like this means it's sticking out, the 2 solid lines are in the same plane as the paper, and the green dashed line is actually sticking back. Now if we enumerate these, then we get 1, 2, 3, and 4. Now these are spatially oriented in such a way that you can actually draw a molecule then that can't be superimposed upon it. So I'll draw that right here next to it, and you can see what I mean, and then we'll try to illustrate what that renders for us. So if we change the position of 2 of these molecules in the first one, you can see then that this molecule will not, you can never take this molecule and put it directly in the same place as this, and they'll be in the same orientation. They are what we call then enantiomers. So these are two. Now some people say that they're the mirror image of each other, but they are sort of, you can think of them as mirror images of each other. So if you want to, you can, I can try to draw this. This is a little bit more complicated to draw, but I mean, if you draw like a plane here, and you imagine that this plane is some sort of mirror, and then you push one molecule in front of it, so we can take this molecule here, we'll use the same colors and just draw it sort of like, and so we'll draw a dashed line back. We'll do a solid line up here, and then the red will be sticking out towards us. Then if we think of the mirror image on the other side of this here, then the other image will be something like, the thing that's going to be sticking out at you in the mirror will be, reflected directly. It'll be turned inside out like a mirror image is. So you'll have the same molecule staring back at you, except for flipped inside out, or so you can think of it as sort of a mirror like such. I don't know how well that is going to get through on the video here, but that's the idea, right? That you have two hands, and that you could theoretically, this hand could be just a mirror image of this hand. And this has a little bit of some issues, and the main thing is that when we look at them and we want to know how they work, or what they are, we want to be able to name them, or we want to be able to identify what type of enantiomer we're dealing with. And the way that we do that is by trying to visualize these in our mind in 3 dimensions. And I'll give an example here of two, actually. So let's flip over and let's do some examples of chiral molecules where we look at enantiomers. So let's look at 2-chlorobutane, which is a good example because we can then look at the central atom here. We can look at the butane and we can say, okay, it's CH2, CH2, and then we have a carbon, all right, that has a chlorine on it. And then we have another carbon after that. And if we draw it sort of as a hybrid abbreviated formula here, we can see that, okay, how many does this have? The chlorine, this carbon has, as we can see, if we prioritize them on the basis of what their molecular or atomic mass, then we know that this one is going to get prioritized 1, and this is going to be prioritized 2 because it's a carbon that then has another carbon attached, and this is prioritized 3, and this is prioritized 4. So remember, the priority rules that were in the earlier part when we talked about the EZ still apply when it comes to this type of stereoisomer as well. So this is an optical isomers. So let's look at this molecule and let's try to draw it in 3 dimensions. And it doesn't matter how we draw it in 3 dimensions in the first case, because we're going to draw both. So I'm going to draw both enantiomers. So let's just draw this one. So in this case, I'm going to draw it a little bit differently than it's drawn up there, because of course we want to have it in 3 dimensions. And then I'll redraw it again for clarity. So here I've drawn it in 3 dimensions, and now I would like to determine what this structure, what type of enantiomer it represents. And I can do that by reminding myself of my priority rules, and then also trying to rearrange this molecule in 3 dimensions. And what often happens then when you do this is you want to maybe simplify the molecule a little bit. So sometimes what I do is I just take and you can do it with color, which I do sometimes, which I'll do in this case. But I will also then number it. And so going back up to the picture up above, we saw that this was priority 1. This was priority 2. And this was priority 3. And this was 4. But I'm going to leave that alone for now, even though it is 4, because hydrogen is always 4. So what we need to do now mentally in our heads is we need to think as if this hydrogen, which has the lowest priority, is moved very, 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 very far back into space. So it's like a different thing. And then we draw the molecule that we would see if we saw if the hydrogen was really, really, really far back. So we're moving this hydrogen back somewhere like this, and then we're going to look at what happens to this molecule. So if I rotate this molecule so that the hydrogen ends up in the back here somewhere, then I can see then that the chlorine ends up here, and the ethyl group, right, which I'll just keep it the way it is for now, you end up with this. So now let's remind ourselves what priorities we gave them again. So we gave the chlorine, because it has the highest atomic mass, we gave it the highest priority. And we gave the ethyl group the next highest priority because it's heavier than the methyl group totally, and particularly because the carbon is followed by another carbon. So then this gets 2, and the methyl group gets the 3rd. So then if we follow this from one position to the next, around like this, we can see that it is going in a clockwise direction. So this molecule is called an R molecule. So this is then, and this is from the Latin word for right, which is rectus. If we look at another molecule of the same type, or exactly the same, but we want to draw both enantiomers. So now I've drawn the R enantiomer, so now we want to draw the other one. So we can just draw the S down here, or the other enantiomer, by drawing something very similar. All right, we take the CH3. Now we need to switch 2 positions here. So anytime you switch 2 positions, you will get a different enantiomer. H and CH2, CH3. This time, I can prioritize, but we can prioritize over here in just a moment. I make this decision. The H obviously is sticking out towards us in this case. So we need to rotate the molecule all the way around to the other side. And since we rotate it all the way to the other side to bring the H all the way back, we need to then try to visualize what's happening. If this goes all the way back, it doesn't matter which way, then the chlorine is going to end up, right, we're going to, so this becomes Cl. And rotating it all the way around, we get CH3, or CH2, CH3 here, and the methyl group here. So if we go through the process of prioritizing then, we have a red back there. All right, and our blue here. And our black here. And if we enumerate them, we get 1, 2, 3. And in this case, then, when we connect 1, 2, 3, it goes in the counterclockwise position. So this is then what we call an S, or sinister. Molecule. Chiral molecules are present all over the place, and it is particularly problematic in some parts of biochemistry, because in some parts of biochemistry we have literally hundreds and hundreds of carbons attached to each other in complicated structures where you can have multiple rings and you can have multiple carbons with many substituents. But even in a simple drawing like the one that I'm about to do now, we can see that the chiral molecules are quite common. So this carbon here, which has a hydrogen attached, then has 1, 2, 3, 4 different things, so it's chiral. This one also has a hydrogen, so this is chiral. This one has 4 attached, so it's chiral. This one has 4 attached, and it's chiral as well. So the number of chiral atoms can become quite complicated in some situations. Okay, this concludes then my brief introduction, or somewhat not so brief, but introduction to different types of isomers. I will pursue some of these a little bit in more detail in a future film. Thank you for watching.